This conference will now be recorded. This conference will now be recorded.
The ways we would know it is for that what we had done was we looked into the mean across different time points, right? We looked at the mean at the average level, at the monthly level. We looked into the mean at the quarterly level, and so on. So we had looked into the mean along this particular trend across this particular line. Now, what we could see over there was that the mean was changing very quickly, right? So the mean changed very quickly. So mean changed over different 9 points, right? At a so at a be at a quarterly level or be it at a monthly level, the mean was actually changing, and that it had a linear pattern to it. So there was a linear trend to this particular mean that we had. Linear trend to this particular uh, variable, right? So one thing that we had seen over there was that then there was a linear mean. So the mean had a linear trend, and hence we said that it needed to be trend. Now then we looked into the data at a quarterly level. So when we looked into the data at a quarterly level, we could see that yes, at a quarterly level, these values were changing. If the values of the were changing at a quarterly level, so we could see that okay, after some quarter the values were kind of repeating, so that the values were higher after some specific quarter, and through that we identified a periodicity in the behavior of the time series. Now if a time series has a certain periodicity, then the challenges that it comes out is with the challenges of seasonality, right? So we could come across that. So that was one. The next thing that we talk about, the next thing that we talk about over here is the overall understanding of the model, right? So we talk about the overall, so we talk about the overall understanding of the way the series could be trended. Right. So in the last session, we talked about identifying the seasonality and the trend. Right. Now, in today's discussion, we'll see how is it that we can remove that trend and seasonality from the data. Right. So that's the next. So that's the part of the discussion that we will be having today. Right. So very quickly, we'll want to understand how is it exactly that this thing can be done. Right, so we looked into the TS seasonal summary and we plotted that, and from there we looked into the average behavior, we looked into the variance and everything. So we saw that at a quarterly level there was a seasonality and that the variance was gradually increasing. So the mean had a linear trend and the variance was increasing over a period of time. which clearly shows us that yes, this time series. So the data generating process of this time series is something very similar to the unit root process that we had already seen, right? So before we proceed, what we are going to do is very quickly we are going to use these two so basically what we are going to do is we are going to use these two things, and from there we are trying to we try to put it out from there. Okay. So very quickly, let us print the data. So we have a seasonal summary over here, and we have the mean summary over here. So we'll just use both these two things. So I'll just open a new Excel sheet over here. Module want methods. Time series. So I'll put the case study one over here. This is the airline case. What we'll do is we'll copy this exercise. Okay. Sorry, I just had. Okay, so let's have a quick look into the trend. So we were looking into the trend of this time series model over a period of time, right? So we were looking into this. This is the average, or let me give a separate heading over here. Trend of trend of the annual average of time of the airlines time series. So I will put it at 10. Add a trend line. So over here, when I put a linear, when I try to fit a linear trend, you can see that there is a 99.66% fit, right? So which clearly shows that this particular time series that we are talking about has a linear trend associated with it, right? So the airline time series clearly has a linear trend, and hence what we need to do is we need to trend that time series. Now, so you have this quarterly indicator, the quarter-wise indicator, and you have the average values over here. This is the quarterly average of the time. So let us we have a loop over here. Okay, so now if I fit a linear trend over here, so even at a quarterly level, you can see that the mean is changing, right? So the mean, so the linear fit has a good hold. Also, what you get to see is that every so the initial parts, right? The variation was much lower than the variation than you see in the later parts of the series, right? So what we'll do over here is we'll introduce one more column over here, which is the standard deviation. So I'll attach one more column over here, the average standard deviation. So what I'll do is I'll take a sample of 10, right? And I see the uh, I see the standard deviation in each. Now I'll do is I'll take a rolling sample of 10 periods, right? Or let me change this to 12 months. So I start from 1949, 4901 to okay. So there are 4 quarters, right? So for each of the 4 quarters, I'll take this for each of the 4 quarters, and on a rolling basis, I'll take. Now, the reason that I'm taking this on a rolling basis is because, so the reason I'm doing this is because, uh, so every time you are looking into a 1 year period, so that window or that time frame remains unchanged throughout. Average trend of the standard deviation. It is rolling 4 quarters. So this is how the standard deviation series looks like. Right now to this, if you want to fit a time series, the first time point when you have is 1904. So now if you look into this time series, the trend of the standard deviation of every 4 quarters rolled over, you will see that this deviation is increasing every time. Now when now the question is this increasing linear? So let's have a look. So what I'll do is I'll put a trend line to this. So what fits this one? One of the things that you can see is that this, so if I try to fit this point over here, you have 87.38. Now what I'll do is, so that means the linear fit is giving you an 87% fit. Now the moment you do it an exponential fit, you see that there is a better fit over here. So the standard deviation is increasing exponentially over a period of time. Now what you are doing is, if I put a logarithmic fit over here, the logarithmic fit is obviously lower because it does not capture this higher end values. So mostly it's a linear fit. I mean, it's a exponential fit which is giving you a 90% fit. So you can say that yes, this line is increasing, or uh, the trend of the standard deviation is increasing in an exponential manner. Now the next part that I have over here is this, the polynomial of the order 2. Now if I do the polynomial of the order 2, the polynomial of the order 2 fit will give me an 89.44% fit, but that is still marginally less than the exponential fit, right? So the highest fit that I can get, right, is, so rather than a polynomial of second order, I can see that it is an exponential fit, which is giving me a better result. If I increase this, still you see it is 89.5% fit, right? So I have increased it to the fourth order, but the R square is not really increasing. So it does not make much of a sense to do a polynomial fit to this. So basically, if you have to approximate this time series, you can see that the best possible fit that you are getting over here is that of an exponential fit. So this is one of the important characteristics of this time, of the stationary, of this non-stationary time series, is that if your time series is non-stationary, then what you get to see is, so what you will see is that this trend of the standard deviation increases over a period of time, right? So this trend increases over a period of time. Okay, so this is something that we have over here, right? So we have this. So one thing you can see that if your time series is stationary, you have a trend in the mean as well as you have a trend in the variance, right? So both these two are not stationary over a period, and they are not constant. As such, this time series is non-stationary and hence needs to be stationarized, right? So is this part clear? Any questions up to this point, Padmini? Perfect. So now the next thing that we are trying to do is we are trying to seasonalize the time series, right? So now we want to uh, like remove the trend from the time series. That's one, and we also need to the trend in the mean, as well as we would want to remove the trend in the variance. Right. So one of the things that we had also seen is that if I look into the ACF and the PACF, the ACF and the PACF gives us a similar result. So we'll just run this and we'll have a look into the. So one of the things that we saw over here, Padmini, is that with without the statistical measures or without the ACF and the PACF plots, so just by looking into the uh, others, so just by looking into this particular plot, I mean, sorry, just by looking into this particular So just by looking into the ACF and the PACF, what we can initially get is so the result that we get by looking into the ACF and the PACF, and the result that we get by not looking into ACF and PACF, that is the result that we get from the intuitive and the from the intuitive exercise. We get to see that they are very similar to each other. So these are the autocovariances. Okay, so this is how it typically now looks like. So one thing that you can see is that if you plot these covariances, right? So I will what I'll do is uh, I will plot the lags and the correlation in a bar chart, right? So I will not be keeping this exercise. I will be plotting it in a bar chart. So the moment I do it in a bar chart, you will be able to better see this. So let me delete this part. Okay. So this is the correlation. Now this is the lag. So just let me. So this is the autocorrelation function. You have the autocorrelation function. Okay, so this is the autocorrelation function. Now, if I have a loop, right? So one of the things that I see is that if I you can see that this is increasing up to a certain point. So up to this lag, up to the eighth lag, it is decreasing. Then again the autocorrelations are increasing, right? Okay. So then again, what you see is that the ACF has decreased up to a point and then increasing, spiking up, and then again going down, and then again spiking up, and this happens at a very regular interval, at a very regular lag. So basically, one of the things you can see is that with the zeroth lag, lag zero is having the highest ACF, so that will be one. Now from here up to a certain up to the eighth lag, it decreases. Then it starts rising from the ninth lag, and then like after 12 lags, you see it again spiking back. Then it goes down again, and then again spikes back after 12 lags. So every time you see that it keeps on spiking up, right? So the very fact that it is spiking up at regular intervals, it shows that yes, there is some kind of a thing. So it shows that yes, there is some kind of a behavior that we have over here. So there is a spiking up behavior every time that we have over. And there is an element of periodicity into it, and because it is happening at every 12 lakhs, so like a gap of roughly 12 lakhs. So what we'll say is that this is so there exists a element of seasonality in this particular bit. I mean, in this particular uh, distribution, in this particular variable, right? So, so the result that we saw through this intuitive analysis and the result that we see through this autocorrelation function is exactly the same. And we can clearly say that yes, there is a problem. I mean, there is element of non-stationarity and that there are temporary components which is creating this ups and downs. Right. So this is one of the analyses that we had done last week, but we just concretized or we just did it in a more exhaustive manner. Now the question is that there is a trend in the mean, right? Now what I need to do is I need to make this non-stationary series into a stationary time series. And this is where I need to pull out those records which are, or I need to pull those out which is not a part of the time series. So which is basically which is creating this non-stationarity. I need to pull out those components from there. And this is where this detrending exercise comes into play. So what I need to do is I need to do two things. One is the YT. So what I need to do is YT A plus BT. Now following this equation, we would get this trend component of the series and subtracting this from the actual value, we would get the trended series. If the trend is a multiplicative trend, then the trend component is divided by the, so basically, then if it is a multiplicative trend, then the trend component is divided by the observed value to get the trended series. Right? So over here, what we are going to do is we are going to do this same exercise. The entire idea is we'll fit a linear regression, we'll get the regression equation. From there, we'll get that values, right? And from those values, from the observed values, we'll get those values which has a trend in there. Now the question is, if I say that there's a linear trend, what do I essentially mean? What I essentially mean is that this yt that I have, or this yt that I have, is or it has a linear trend, or it is a function of time. So the yt is equal to a plus bt. So yt is just a function of time. So what we are trying to see in this trend is, if I have to identify the trend component, what I want to understand is that independent of all the other characteristics. So independent of all the other characteristics, how much, right? So independent of all the other characteristics, how much of this yt is solely driven by time? That is all that I want to see, right? So over here, what I am trying to see is that if this part is to be removed, so if this is something which I should uh, so if I can remove this variation of this value of yt, which is solely being driven by time, then yt is equal to a plus bt. Okay. So what we'll do is we'll first I try to identify the value of yt which is changing as a result of time. And then following this equation, we would get the trend component of the series. And then we would subtract this to the actual value. We would get the trended series. So that's the exercise that we will be doing. Now, what we need to do is, because there is some element of repetitiveness, right? I want to find out the so what I am trying to do over here is I am just trying to find out the so so over here what I'm trying to do is I'm just trying to find out the time component, right? And once I have identified the time component, then what I'll be doing is I will be modeling the passengers. So what we are doing over here is the following. So let us follow this one by one. Okay. So what I want to do in this exercise is I have this data set called airlines trend. Right? In this airlines trend, I'm creating a summary. What am I doing? I'm saying that okay, I need the observations, and corresponding to each of the observations, I need the so I have the records, and corresponding to them, I need the observation number or the time. So basically, the first observation, so 1940, the first record will be given the value 1. The second 1949 will be 1949 Feb will be getting the value 2, 1949 3 will be getting the value 4, like this. We will be associating values to each of these inputs, right? And then what we will have is we will have the time period, the value, and the time. So in a data set, so the data set would finally look something like this. So it will have Jan 40, 1949. I'll have the passenger number. I'll have the time t. So basically 1949 is assigned the value 1. 1949 Feb is assigned the value 2. The 9 is assigned the value t. So this is the first time point, second time point, the third time point, like this. So basically, if you see this Jan 1950, right? So it is a 13th time point, right? So that's yes. So okay. So Padmini has a question over here that can it not understand the date? Yes, it can understand the date, can read the date. But what we are trying to do is we are trying to estimate a relationship between the time point and the passenger. So I'm trying to write a regression of the form. So I'm trying to write a regression of the form yt is equal to a plus b dot t, time point, right? So now time is the date. So over the you have the date. Now what I'm trying to do is I'm trying to convert that date into a time point, a value. So it's the, or the order of the time period that is there, right? So that is what I'm trying to do over here. Okay, so what I'm trying to do over here is I'm trying to find out that better. So what, how am I doing this? So let me run this code. So first what I do is I create a blank data set airline trend. Right. So first I create a blank data set over here. Now to this data set, I will be taking up each of the records and I will be putting them one by one. So now what I want to do is I want to take out each of the records and assign a time period value. The very simple way I am doing it is I'm saying that TS is airlines is first observation. So over here, first observation specifies the point from where you want to start reading the data. And observation specifies the point up to which you want to read the data, right? So what you have is the point from where the data set needs to be, from where we should start reading the data set. So this is the point up to which data set has to be read. So the logic over here is if we are reading the first and the last point of the data as the same data point, then the output is then the output is one single object. Okay. So this is the first thing, right? So what I'm doing is by assigning the first observation and the OBS value as the same value. So first OBS is the point from where we are starting to read a data set. So that's the first observation from where we'll start reading. Now the observation is that value from where up to which we will read. Now the next thing that we have over here is so what we've done is we've identified one record. Now to that record, what I'm saying is assign the value T. So I'm fetching out one record at a time, right? And I'm assigning a value to them. So the first value is T, the second value is T plus one, then 2, 3, 4. Now this can easily be also done through a counter, right? So we can write a counter and a loop and we can generate this value. So I have done this because this will give you a step-by-step exposition of the entire exercise. Now what we are doing is we are running this, we are setting this value as val, so this T as this variable. So the so over here, when I'm running this T equals to val, what we are doing is, or what we are saying is that, hey, look, that this is the time point that I have, right? So time point is, so for the first observation, the val is assigned the value 1, the val variable is the value 2 in this, 3 for the next, 4 for the next, and like this it will go on, right? So now what will happen is, so now if you go to this airline trend data, you will see that it is Jan 1949. You have the passengers, month, year, quarter. right? And the time period is assigned the value t equals to 1. So it means this is the first time point, and corresponding to the first time point, the passengers that I have is 112. So over here, then what you see is that to that data set that I had created, the next row gets appended to it. So now I am getting the master or the summary data set. So to the second data point, that t equal to 2 is assigned, right? So like this has to be, so this will be going down. And we'll have it till 144. So we can obviously yes automate this further, but I have just kept it this way. So what I have done is I have written this macro, this small little macro, and I'm running it for all the values over here. Now, one thing that we can also do is we can actually use a counter and we can generate all these values through a loop, and then we can be calling the macro like that. But so what I am doing, so what like I am doing over here is I just want to put it over there. So I just want to kind of make this simple so that you can run whichever the macro for whichever value you want, and you should be able to see how it is working. So over here now, what I have done is I have created this data set airlines trend, which has all the observations and it has the corresponding 9 points to it. Right. So now I have two series over here. One is the YT series, which is the passenger series, and I have the time series, the time point. So now what we'll do is we will run a linear regression. Now, why are we running a linear regression? Because we want to find out how what is exactly the level of causality between so how is it that this passenger and the time point is related to each other? So what we are doing is we are developing a very simple linear regression between passengers and time, because we have already seen that there exists a linear chain between this time series and those passengers and the time series, right? I mean, the passengers and the time. So now, if you have a look into the regression results, we'll see that the adjusted R square is 85%. So all these values, the variation in this YT, 85% of the variation is explained by the time component, right? So whichever time point it is. So this mean is more driven by the movement in time than anything else, right? So what is the idea like over here? The idea is like this, that there is a very strong positive association between time and the dependent variable. I'll not use the word association, it can be misleading. A strong causality between time and the dependent variable passengers. 85% of the variation in the variable value is explained by time. Now, this is the temporary component to and cannot be relied upon for long run prediction, because if your trend is, if your mean is changing with time, right? Now, let's say, so it means you don't have any variable or historical lags explaining your movement. So it's just that the change of the time, and if that relationship gets disturbed somewhere, then your predictions go haywire. So what you need to ensure is that before you do this exercise, so before you add or before you work with this, what you need to do this exercise is you need to work with uh, so So there is a positive strong causality between time and the dependent variable. So what you need to do is you need to ensure that so you need to ensure that the passenger. So what we need to ensure is that this trend component, the impact of time, is removed from the YT series, because after that is removed, the remaining part, which the values that remain back, is will be because of the fundamental behavior. The remaining 15% of the value is something which will be because of the fundamental behavior of the time series over a period of time. That's a more permanent behavior. So this behavior is like a trend behavior, which is being largely driven by time, right? Right. So now what we are going to do is, the equation that I have over here is 87.65270. Uh, okay. I'll have out ES. So this will give me the exact regression coefficients. So I will say this is ES dot trend regression distance. So I have this trend regression distance. You can see that the intercept is this. This is the intercept value. Now this value is something different from what you can see over here. This is a more rounded off value, and the exact parameter estimate value is this. And this is the exact uh, statistic. So this is the value of the predicted values of the passenger. So one thing you can see is the passenger value is 112 over here, out of which just by regression, trend regression, I can see 90 is due to trend. Similarly, 118, 92 is due to trend. Out of 129, 98 is due to trend. Out of 121, 100 is due to trend, and so on. So now if I subtract this part, which is due to trend regression, if I remove that part, then the series that I will get is, or the subtracted series that I will get is, or the subtracted, or the, I mean the remaining series that I will get will be your so basically that will be your passenger counts, right? So that will be your detrended series. So let's say, for example, over here I have 140, and over here I have 151. Now if I subtract this, it means that this turns out to be negative, right? So but however, we cannot have negative number of passengers. So what we'll do is, we will look into this descended passenger series as a ratio rather than as a difference, because that difference can lead to negative values of passengers, which is not really possible. So we would say that, okay, the entire thing has been due to trend, and then we would need to cap those values at zero, but that's not possible really, right? So we'll start off with this exercise. So in this airlines detrended series, we will run this passengers detrended is equal to passengers, the original value of passengers divided by the value due to trend. So the remaining part of the series will be your detrended passenger series. So this is the airline's detrended series. So this series gives you the idea that okay, this is now the remaining. So after I've adjusted the series, so I have taken the ratio. So all I'm saying is that the original value of the passengers was 1.24 times that of the value due to the trend. So this 1.24 is now adjusted to the trend because you have already divided it by the trend figure. So you have kind of divided, or you kind of have taken care of those parts which was because of this series, right? So now what you have is the detrended passenger series. Now what we'll do is we will run this detrended passenger series on the time series. So now if I do that exercise after removing this, okay, we can also do another thing, try out both passengers detrended 2 is equal to passengers predicted, sorry, actual minus passengers predicted. You have passengers detrend, you have passenger detrend too, so there are negative values as well. Right. So basically what we are saying for these values is that okay, whatever the value was, it was because of this trend, and after we trended that, nothing remains. So basically it be capped at 0. So anyways, we'll look at both. Right. So first what we'll do is we'll do this regression with respect to the detrended series. The first one, the multiplicative trend that we have looked in. Now over here you see that the R square of this series is 0.02. So just only 2% of the variation is now explained. Also what you see is that this p-value is now more than 0.05. It implies that this time series t is divided by is independent of this series, right? Okay. So any questions up to this point? So only 2% of the variation, only of the variation is explained by the time series, by the movement. This is the final trended series. So over here again, if you see the p-value exactly what this series is one, so I use the difference series. That too is detrended. You can see that the adjusted R square is one negative, right? So the R square is 0, so no variation is explained whatsoever. So this series now is absolutely independent of time, right? So now let's have a quick look into this series, so how this series is looking. So we'll go ahead initially with this ratio of this multiplicative trend, right? And then from there we will see. So over here, what we are doing is we are just trying to plot the detrended series over here, right? And we have the passengers detrended and all these things out here. Right. So now when I plot this series between the passengers detrended series and time, right, you see that this is how the series. So there is no definite pattern whatsoever, right? So this series is completely independent of the impacts of time. Versus if I had plotted passengers and time, let's see how that would have looked at. So when I plotted passengers and time, this is how it was looking. You fit the linear trend and you get the series, right? So let me also do this passengers predicted. So this is how the predicted values and it looks like. So it looks like a clear straight line, right? And over here, after you have detrended, this is how the series looks like. You can see a clear difference between the pre-transfer, the pre-trending series, pre-detrending exercise, and the post-detrending exercise. And we can clearly see it over here that yes, after detrending, the series is looking very different from what it was essentially looking. the detrending exercise. Right. So this is how the trending exercise actually works. So any questions up to this point, Padmini, on this trending exercise? Perfect. So now the series that we have already removed all kind of trend components from the series. Now over here, now the next question which comes over here is that how do we assess the seasonality? So now I have a trended series. Now what I want to do is I want to do some kind of a prediction. So now that this series doesn't have this pattern, so what I want to do is I would want to do a an ACF test, right? Autocorrelation function test, and using that ACF result, I would like to see how this different. So is the problem of seasonality solved till now, or still do we have that problem of seasonality over here? So that's something that we want to judge, or that's something that we would want to see over here, because after, so does descending the series solve the problem of seasonality simultaneously, or do we separately need to solve the problem of the stationarity, right? And while we are doing this over here, now the next thing that we need to bring in is the next thing that we need to bring in over here is that we want to understand how the so over here what we would want to do is we would want to bring in the ADF test results. So we need to interpret that as well. So till now we have looked into the intuitive approach of identifying seasonal stationarity. We have looked into the so we are looking into that, and also we have looked into the ACF approach, right? And we have defended the series, but we also need to look into the ADF test results. We need to understand how to interpret the ADF test results, because that is a very important part of the that's a very important part of the analysis. Okay. 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 So what we'll do is we'll very quickly on the passengers detrended variable, on the detrended passengers variable, we'll try to see whether there is stationarity or not. Now on the detrended series, I am applying this. Now the moment I have applied this, one of the things that you can see is that the correlation pattern has now directly changed, right? So given that the trend has been removed from the series, the pattern of this movement has totally changed. So this ACF has totally changed. Now that unique positive correlation which was there across all the time points, right? What now we can see is that they are alternating between each of them. Right? So they are actually alternating between these two time points. They are so So across different lags, it is becoming, at times it is negative, at times it is positive. Now that continuous positive characteristic was because of the existence of trended this trend in the time series model, right? So over here now, if I try to interpret this result, so there is a 35%, 35.35 goes down to 11415, again comes back to 0.20, then goes down to 0.5, 0.4, 0.4, 0.47, rises up, goes down, but again from the 10th or the 13th lag, you can see. So in the 12th, in the second lag, the color was 0.15, 0.1512. Now, after 11 months, so 11 months down the line, you see the correlation is again spiked back to 1.50. So over here with the first lag, it was 0.35. Over here, it is something close to 0.35, right? So it shows that from 1 to 12, right? So every 12 months, this again spikes back, right? So there is a rise in the spike of the time series. So in the ACA patterns. So this clearly shows that the even after detrending, so after detrending, that continuous positive relationship has gone because of the continuous positive trend. So once I've removed that component, now the seasonality still persists over there. You can see that by an occasionally increasing autocorrelation coefficient. So the next question that comes out is how to remove the seasonality from this time series, right? So the next question that comes out is to deseasonalize the time series. Okay, so any questions up to this point? Okay, so what we want to look into is that whether so how is it that so are the autocorrelations statistically significant over here? So one thing that we can see is that yes, the autocorrelations are pretty statistically significant, right? And that we can see that the autocorrelations were spiking up, which shows the existence of seasonality. So these are some of the important interpretations. Now the next question is that before we move on to seasonalize the time series, right? So till now we have been looking into different measures. Now we also need to look into the augmented DP fuller test statistic. We need to understand that how is it that this augmented DP fuller test statistic is trying to help us interpret the existence of non-stationarity. So which is, so we'll start off with this exercise in tomorrow's discussion. And tomorrow, Padmini, I may be working, so I'll not take the risk of pushing your class to 11 or 12. I'll first, right at the first hour of the day, I will finish your class from 8 to 9:30, and then I'll start off my day. So 8 a.m. works for you? Okay, that will be great. So then I'll start off with the class from 8 a.m. and I'll finish it up by 9:30, and then I'll start my day because I may have to work tomorrow. Right? Okay. So thank you, Padmini, and I'll share over this Excel sheet with you once I close the session. Thanks a lot.